Another early application of definite integrals is something called the mean value theorem for integrals, which also leads us to something called the average value of a function over a closed interval. We're going to look at the mean value theorem for integrals in this video, talk a little bit about the average value of a function near the end of the video because they're so closely related. But then also I'll post another video that does other examples of the average value of a function so that you can see it more in depth. So let's start with the mean value theorem of integrals. Now remember, there was a mean value theorem for derivatives, and that's been posted in an earlier video. This one is the mean value theorem for integrals. So the mean value theorem for integrals says that if you've got a continuous function on a closed interval, so remember your function here is continuous. When the brackets are used to start and end the interval, that means the endpoints are included and we call that a closed interval. Then there exists a number c in the closed interval from a to b. So your c is an input value that you would put through your function such that the definite integral from a to b of f of x dx is equal to f of that number c that exists that it was talking about up here. So this is the output when c is run through the function times the length of the interval, so times the difference of b minus a. So your definite integral from a to b of f of x dx is equal to your f of c multiplied to the b minus a. Now let's see how this kind of makes sense when we think of it graphically. Over here I've graphed a function and I've denoted the vertical line starting at a, ending at b, so over my interval. Now recall the definite integral from a to b of f of x dx adds up all the function values. So from the x-axis to the function, it adds up all of these values. And when I have my graph non-negative over the interval, that actually represents all of this area caught between the function and the x-axis over the interval. So all of that amount here is what we're talking about when we get the number for the definite integral from a to b of f of x dx. So that's this side of the equal sign. Now imagine you had two pieces of plexiglass that were very close together that started at A, ended at B, and had like a groove that had a wire that would conform to your function in the two pieces of plexiglass that are really close together. And let's say that you have water or some sort of colored fluid that would be in this region of those two sheets of plexiglass next to each other. So now, what if you took and you tugged that wire and you pulled it out from between the two pieces of plexiglass? Well, what would happen would be that this liquid that you would have would level out and you would get that rectangle of the colored liquid in place of the curved part because water is self-leveling, or liquids are self-leveling. Now that makes a rectangle because we have our vertical line at x equal a, our horizontal axis for the x-axis, our vertical line at x equal b, and then that top part now leveled out when you pulled out the wire. Well, I can find the area of a rectangle from my geometry formulas. The area of a rectangle is my length times my width. So if I look at my length being how tall this is, that would be, let's do it over here. So that would be how tall it is, and then how wide it is, that's going to be the b minus a. Well, how tall is that? What this mean value theorem is saying is that there is some place in this interval, at least one place in this interval, where that leveled out liquid would intersect with the wire if the wire were still in there. And we can see that visually in the picture that I drew here. That leveled out liquid is intersecting with the function right there. Now, that point brought vertically down will be a value in the interval from A to B. And that value is what you're calling the C that's in that interval from A to B. And then running that C through the function is how you get the height of that dot where it intersects the function. So that is your f of C, which also ends up being how tall the rectangle is. So this is the area of the curve before you pulled the wire out. And then after you pulled the wire out, you have your how tall the rectangular area is times how wide the rectangular is for the area. And that leveled out area is going to be exactly the same as the area that conformed before you pulled out the wire. So that's basically what this is saying. Now you want to make sure you realize that this f of c is a value you get out from the function when you run the c through, and this b minus a is the length of your closed interval. So those are two values that are multiplied together. And then this definite integral from a to b of f of x dx, that's a number. So then if I wanted to find the value of c that's guaranteed by the mean value theorem of integrals, I would have this left-hand side be a number. I would have b as a number, a as a number, so b minus a would be a number. And this f of c, I would just put c's through where all the x's are in the function, and that would give me an equation to solve. But remember, you just want to report the c's that are in the interval. So now, when we talk about the average value of a function, on the closed interval from a to b, really what you do is you take this equation you had from the mean value theorem of integrals along with its condition, and you solve for f of c. So solving for f of c, you're going to just divide both sides by the b minus a. So it's f of c is equal to 1 over b minus a. Dividing by b minus a is like multiplying by 1 over b minus a times the definite integral from a to b of f of x dx. And because this is the focus of the average output, what the height is, then they write this as f with a subscript of abbreviation avg for the function average. So f sub avg is my 1 over b minus a times the definite integral from a to b of f of x dx. So when they just ask you to find the average value of a continuous function on a closed interval, don't get too worried about a whole bunch of different stuff that you have to do. You just need to find your definite integral over that interval and then divide by the length of the interval, or multiply by the reciprocal of the length of the interval, whichever way you want to think about it. It's just solving for the f of c. The average value of the function focuses on what is that height output at that leveled out value. And the mean value theorem of integrals focuses on what is the c input value that would run through your function so that it would create that average height. So the mean value theorem for integrals is looking for actually the input value in your interval that would create that average height, and then the average function value is just actually looking for the average height. I've kept the mean value theorem up here so that we can see how we have to go about it. This first example says to find the value of c guaranteed by the mean value theorem of integrals for my function f of x is equal to 9 over x to the third on the closed interval from 1 to 3. Now 9 over x to the third's domain is all reals except 0. 0 is not in our interval, so this function is continuous on our closed interval, and it's a closed interval because it has the brackets. So our mean value theorem says this definite integral from a to b of f of x dx, so for our problem it's the definite integral from 1 to 3 of 9 over x to the third dx is equal to f of c. Now f of c, we need to go to the function, take out the x's and put in c's instead, and we don't know what c is. That's what we're trying to find. So here's my function, here's my x's. I'm going to write for f of c 9 over c cubed, and then that's multiplied to b minus a, but I know b and a is 1, b is 3, so this is 3 minus 1. Now this left-hand side is a number. It's really important that you remember your definite integrals are numbers. So I have to figure out what that number is, and once I find out what that number is and simplify this equation, I'll find the values of c and only report the ones that are in the interval. Now integrating this definite integral, I need to find an antiderivative of 9 over x to the third, so think back when you were doing the indefinite integrals, but don't add the plus c. After that, we're going to plug in our endpoints. So we think that's a definite integral from 1 to 3 of 9x to the negative 3 dx. And on the right over here, I have 9 over c cubed times 2. Now, integrating this for our thinking of finding our antiderivative, letter base to number power, and times a constant. So we're going to add 1 to the exponent. Negative 3 plus 1 is negative 2. And divide by that. So that's 9 over negative 2, x to the negative 2, evaluated from 1 to 3. And then on this right-hand side, I have 18 over c cubed. Now we're going to put that x to the negative 2 back down in the denominator, plug in the top number, minus plug in the bottom number. So think of this as 9 over negative 2x squared down in the denominator. So it'll be 9 over negative 2 times 3 squared minus, for the Fundamental Theorem of Calculus, 9 over negative 2 times 1 squared is equal to 18 over c cubed. And what we did here was our definite integral from a to b of f of x dx can be found by f of b minus f of a, where capital F is an antiderivative of small case f. So then this is 3 squared. So I have 9 over negative 2 times 3 squared. Well, that simplifies to negative a half. Minus a negative is plus. And then this gives me plus 9 halves. And that's plus 9 halves. And then negative a half plus 9 halves is 8 halves, which is 4. So I have 4 is equal to 18 over c cubed. Multiply both sides by c cubed. I get 4c cubed is equal to 18. Divide both sides by 4. C cubed is equal to 18 fourths, which is 9 halves. And so when I take the cubed root of both sides, I get c is equal to the cubed root of 9 halves. And then if you go ahead and rationalize your expression, I need a perfect cubed in the denominator. So I'll multiply top and bottom of this by 4 to get a cubed root in the perfect cube in the denominator. So I have c is equal to the cubed root of 36 all over 2. Now, the cubed root of 36 over 2 is a value in this interval, and it is the value that if you put it through the function, you would get out the average value of that function over that interval.